Okay, we're going to continue. Genesis, can you confirm me that you can listen to me?
Yes.
Okay, thank you. I'm going to share this. Can you see my screen, my PowerPoint?
Yes.
Okay,
but it's not
thanks.
full screen.
Now, is
Yes.
it full screen? Okay. This example, it's a PDF version of this. You have it in the announcement section of the city web. Okay, so let's consider 3 cases of this beam. It's a clamped beam, and it has a uniform load applied on it. So let's see what we can do. So we're going to do 3 cases, okay? The simplest is just to take this load and apply half of that into here and forget about moments. That's the first case. The second case is apply what we have derived in here. And what we have derived here is that this distributed load, okay, will be transformed into an equivalent force and also an equivalent moment on this end. And finally, we're going to do this analysis, but using 2 elements. Okay, so I'm going to include a joint here. And I'm going to apply the equivalent forces and moments process and do it again. At the end, we will be able to compare these results with the analytical solution, since this is a very simple case. Okay, so we'll have the whole idea. Okay, so this is the model. Instead of having anything here, we have only one single value of the force on the right end downwards. And that force is equal to the total force, PL, divided by 2, applied here. That's the simplest case. So let's use these values for the properties: yaw modulus, inertia, length. This is EI over LQ. This is something that we need for our calculations. And the 2 diameters, we're supposed this is a tube. Okay, this is the stiffness matrix. Okay, and for the load, the value that you see here, I just considered that I had a certain pressure value, and I assumed that the spacing between the stiffeners were 2 meters, something like that. It's just as simple as that. That's it. So I got this value, which is rounded up, is this one here. Now, this is the model that I'm going to use. So since we have no displacement, no rotation, what I do is I take this stiffness matrix and replace this value and that one by a very large value, in this case, 1 to the 20th. Okay, so these are the equivalent forces. In this case, since in these 2 positions, the displacement are 0, I take this 1 to the 20 times 0 here and there, and they both are 0. This is the multiplication of this 314 times 100 and divided by 2. That's how we get this value here. And there is no moment on the end. Okay, so that's something that we tend to do. Okay, we have a distributed force. We get the total force and we divide it in 2 parts, and we place half of that in each end, on each end, but we forget about the moment. This is what we are doing right now. Okay, this is the result. Of course, we get very small values on the left end because it's clamped, and this is the displacement, vertical displacement, and this is the rotation. Okay, so if this is X, okay, this is Y, okay, and this is positive for the rotation. So if we have this displaced like that, we see that the slope is negative. Okay, so we have this displacement, this rotation, and these are these two values here. Okay. Equivalent forces, what we do is we take this and multiply by this matrix, the original matrix, and these are the external forces that we obtain. We see that we recuperate the two external forces on the end. There is no moment. So this is the reaction directly, and this is the moment reaction on the clamped end. That's it. That's the simplest case. Now let's try to apply this concept of equivalent forces that we have deduced using this minimum potential energy approach. So let's take this. Okay, so we have a, remember we had this distributed force. So we have half of that into here, and then on this end, since we're pushing downward, you're going to have a moment like that. But on the other end, since this is pushing downward, we're going to have this moment like that. This is X. This is Y. Okay. So this is positive. Positive is counterclockwise. So this is positive, but this is negative. Both external forces I pointed out are pointing downwards, so both are negative. So the stiffness metric is the same, and we have already replaced these two values by this large one. This is the equivalent forces. And you see, this is the big difference. So on the right end, this is positive, and this is positive here. This other force is the same as we had before. There's no change. It's half of the total, which is this one, downwards. We can solve it like this. Again, displacements are very small, extremely small, basically zero. And these are the displacement on the right end and the rotation. Signs, we assume that they are correct. We multiply this, not times this, because we have altered these two values. We multiply this by the times the original stiffness matrix, and we got these are the external forces. Okay, these two values correspond to this, and these two here. This value here, this is the total external force that you need to apply in this point in order to have equilibrium. Okay, so this is equal to what? Is equal to minus PL over 2 is this external equivalent force, and plus the reaction at 1. So that means that the reaction and this end has to be equal to this value, 15,692. Jesus Christ. And then we put this on the other side, so it's going to be plus. And this value is equal to this one. So it's going to be 692.8 or something like that. So that is going to be the reaction. So we're going to have at the end, this force here, and the reaction here. So the reaction will take care of this plus that. Makes sense. So you can do something similar for that in order to have the moment reaction in here. Ms. Larrea, I think you were asking me about this. This is what I tried to explain you. Okay. So you can do something similar for the moment. Okay, now here, these are the values that we obtained with model 1. So this is model 1. that is considered only one force on this end. Okay, so you see here, this is minus 0.22, and this is minus 0.16. So the displacement, it's a big difference. There's a big difference. See, you got 0.16, 10% will be 0.06, so 0.016. So if this where 0.18, the difference will be 10%. But the difference 0.22, though, so the difference 0.05. So it's probably about 30%. So that's a large difference. In the rotation, it's even worse. So you have this compared to that, that's 50% difference. Okay, so that's a big difference. There is a problem here. People, what's the boundary condition on the right end in this case, in the correct one? So I have this, I have that. What's the boundary condition here? Mr. Zambrano, what are the boundary conditions on the right end? Mr. Zambrano, can you hear me?
Yes, doctor.
What are the boundary conditions on the right end of this beam? Don't tell me.
The shear force is 0 and the moment is 0.
Yeah, so the bending moment is 0, and the shear force is also 0. And the problem is that here, we have concentrated forces on that end and concentrated moment. So that's error. That's error. And that's because we're using a very simple model, one single element for this problem. That's error. We have to be careful. So let's go now. Now, we have seen that there is some differences between the two models, right? Because the first one was extremely simple. This is better in some sense. We'll see that in a minute. But still, we see that there are some problems here. Because at the end, the bending moment should be 0, and it's not. Now, let's take another step. Let's put one joint between these two and use two elements and see what we obtain. So this is the model. If we have the load down here, okay, we're going to have a moment in this direction for this element. But also for this element, we're going to have a moment in the opposite direction and the same value. So the two will cancel. That's why you see that here we have no net moment. On the right end, this is PL squared over 2. But now you see that this L is half of that, of the one that we have before. So if we square it, this value will be 4 times smaller than the previous one. For 4 times. It still should be 0. So when we get a very short, very small length for this element, that will be closer to the correct one. But in general, this value is 4 times smaller than the one that we have before. So we're getting close to the exact solution. Okay, so these two cancel. I still have one moment here, another moment here, which is combined with the reaction and all of that. Also, we have some force in this joint equivalent in this element and something similar for this other. These two values add up, and this is what we obtain. So we have a quarter, half, and a quarter of the total load. So let's solve this problem. So this is the stiffness matrix. Now we have 3 joints, 2 degrees of freedom per joint. So we have 6 by 6 matrix. We change these 2 elements of the matrix. We replace them by very large values, and we solve it. I'm sorry, before that, the equivalent forces on the end, this is K big K times the value that I desire, which is 0. Same thing here. And this is the external force. So in joint 2, there is no moment because the 2 cancel. This is the moment, I'm sorry, this is the force here. And this is the force here, which is half. This is half of that. And this is the moment on the end. And these are the solutions. Again, these values are very small, and these are negatives. This is much larger than that one, as it should be, because this is a clamped beam, so you can have a deflection like that. So at the end, let's compare between these two and also with the analytical case, because this is the simplest case, we can solve it analytically. These are the external forces. Again, we could have this force is going to be equal to PL over 4. This is negative, and plus the reaction. So we can take this to the other side and evaluate the reaction. Analytic solution. In this case, the bending moment on the right is 0, shear force on the right is 0. We have minus P constant, we can integrate twice, and the bending moment is going to be a quadratic, we see here. So we evaluate it on the right end. So for x equal to L, this is 1, this is 1. So we have 1/2 here, 1/2 there. So it's plus 1, minus 1 to give you 0. So this is the summary. So this is the red one. The red one is the equivalent, the case when we have a, well, this is negative because I prefer to see numbers in positive. The analytic solution is this one. And the green one, using 2 elements, is this one. And you see here that the solution is not complete. I don't know what I did here, but it seems, oh yeah, because I have no bending moment on the end. So this is using 1 element, but also the considered only equivalent force. Of course, there is no moment on the right end. That's why we end up here. And the red one is using 1 element, okay? And you see that the bending moment on the right end is not 0. So there is a big difference. And you see that with 2 elements, we are very close to the correct one, very close. This is the function. We integrate these twice. And of course, on the left end, the deflection has to be 0 and the slope has to be 0. And this is what we obtain. And we can proceed in order to compare results of the, results for the deflection. This is the deflection using only 1 concentrated force on the right. These two are using the consistent equivalent forces and moment. So when we have equivalent forces and moments. And this is when we have only equivalent force. And you see this is a correct solution or the analytic solution. So when we have equivalent forces and moments, okay, we can expect the displacements in general to be very close to the analytic one. But the distribution of internal forces, as we can see here with the red one, is not that one. It's not that good. Remember the shear force. I don't have it here, but you can draw it. The shear force inside every element, our beam elements, is going to be constant. And the problem is that in the case of this distributed force, the shear force is going to be on a straight line. So there's going to be a variation. So it's going to be a large difference. Okay, so the message here is in general that when we have distributed forces, we should be careful, okay, using finite elements. We should care about convergence, always, 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 always. In general, if we apply this process of equivalent forces and moments, not only forces and moments, we can weight the displacements to be very close to the analytical values, because the equivalent forces and moment are statically equivalent to the exact distributed forces. But since we care only about displacements, in between, inside the elements, we can expect some differences in internal forces, okay? That's why we should worry always about convergence. Any questions about this, people? Any question about this process? I hope you have everything now under control. Is there any questions? No questions? Okay, if there are no questions, then I will stop here, make another break, and when we return, I would like to see if there are any questions about the project, okay? So I'll stop this.